All right, folks, we've been sorting acids into strong and weak, and acids and bases into strong and weak, actually. And now we have the last part of this lecture section is sort of fine-tuning that. Can we say relative weakness or strength of acids and bases? So I'm on page 10.13, and I have this table that's not quite complete. What I'd like you to do is fill in the blanks with acids and conjugate bases. Why don't you stop the video and do that? All right, you stopped it and filled it out, right? So you said, okay, the conjugate base of HI is just I minus. The acid for this conjugate base, HCl, and so on, SO4 2 minus, and that of course is sulfate. Here, the acid HNO2 dihydrogen phosphate. Well, we have to know chapter 3. Dihydrogen phosphate's normally PO4 3 minus, but when I add an H plus, and hydrogen phosphate HPO4 2 minus. Okay, now you'll notice it says strong, weak, and even weaker. So here's what I'm going to do. The trend for this list of acids is this direction is stronger acids. So weakest acid on the list is water, hydrogen phosphate. Strongest acids are actually all of these that we've been categorizing as strong acids from the very beginning. Now over here, conjugate bases, of course, are basic, and there's a trend here as well. The trend over here looks like this. I'm going to draw a line. I haven't put an arrow there yet. Turns out it's that direction. Stronger base in that direction. So if I zoom out here a little bit, stronger acids go up, the conjugate bases go in the opposite direction. And then there's a note I want to make here. These 6 or so are not basic. They're not bases. Okay, so we can summarize this at the bottom of this page. The trend in terms of acid strength, relative acid strength, and relative conjugate base strength, we say they're opposite. Stronger acid correlates with the weaker conjugate base. I could say it the other way. Weaker acid correlates with the stronger conjugate base. We don't have to think of it that way. We could think of these as being bases and these being the conjugate acids, or these are the acids and these are the conjugate base. Either way, we can talk about it. Now let's look at the next page then. And I'm going to just repeat this. Well, there's my increasing acid strength. So I'll put increasing base strength. And I'm just repeating this here. What's the relationship between the strength of an acid or base and its conjugate? We're going to say they're opposite. Or maybe we'd say they're inverse. So now we can say, well, here are some acids or bases, and we can actually compare the relative strength. So if I look at water versus NH4, ammonium, there's water, there's NH4, stronger acids NH4. Sulfuric acid or acetic acid. Now again, this is that acetic acid where the convention is we put the H on the end. I apologize, it just happens. Well, I know that's a strong acid, so I don't even have to look this up, but for completeness, there's acetic acid, and of course, H2SO4. There's our strong acid. HCN, H2CO3. Here's H2CO3, and here's HCN, H2CO3 is the stronger acid. So in the past we would have said, oh, that's weak, that's strong, that's weak. We wouldn't even talked about water being an acid or a base. And there's ammonium. Now we know that's a weak acid. We have a way to sort of sort those out from this list. Now here it says, I want to know the stronger base in each of those. So what I have to do is look for the weaker acid. So I look at HF versus HBr. HF is weaker, which means fluoride is the stronger base. Similarly here, I think, well, what's the conjugate acid for hydroxide? Water. Conjugate acid for hydrogen carbonate, H2CO3. Well, I go to my list. Water is the weakest acid that we can have in water. So the stronger base is hydroxide, which we'd already memorized anyway. But there we go. From our list, picked out the stronger acid. Here we just went backwards, looked at the weaker acid, and that gave us the stronger base. Now, there's a way to do this mathematically and quantitatively. I'm going to go back to chapter 7. Remember K equilibrium, products over reactants? So KEQ would be the concentration of cyanide times the concentration of hydronium divided by the concentration of HCN. Remember, we leave pure liquids and pure solids out, so it's sort of like putting a 1 in there. Now, there's a shorthand version of this. We might write it like this. There's the concentration of cyanide. And sometimes we'll say, well, let's just count the number of protons that have sort of broken off. HCN. These two things really mean the same way. This is just sort of a shorthand. Well, of course, now every time I look at an acid, I can look up its K value. If it really reacts with water, K is big. If it doesn't react with water much, K is small. So I can go to a table and look up these values. Well, HCl is a strong acid. It's infinite. HF, I'm just going to a table and looking that up. HCN, 10 to the minus 10. I'm just looking that up in a table. So there's my strongest acid. There's my weakest in this set. And HF is somewhere in between. So I'm just looking now at that equilibrium value. We use Ka. It's exactly the same thing as KEQ. We just use Ka for acids. Now we can use these Ka values that tell us the relative strength of the acid to think about the relative strength of the conjugate base. Smallest Ka, weakest acid. Smallest Ka, strongest base. So, again, they go in the opposite direction. And so I have this little box here. Stronger acid, larger Ka. Weaker acid, smaller Ka. And look at table 10.3. There's a whole bunch of Ka values typically for the weak acids. And there's a problem here at the bottom of the page. It says benzoic acid, Ka, citric acid, Ka, and then here is the conjugate base for benzoic acid and the conjugate base for citric acid. So I don't know anything about those bases, but there's my benzoic acid, Ka. There's its conjugate base. Citric acid, conjugate base. This benzoic acid is weaker. Smaller Ka value, which means then that its conjugate base is stronger. It's that simple, really. All right, let's look at 10.16. Here's another way to think about this. We have the Ka values, but here's something else that happens that we can measure. So I've got a bottle of 0.20 molarity HCl. I drop it in the bottle, it reacts with water, and I get chloride and H3O+. Well, notice what happened. I started off with 0.2 molarity HCl, no H3O+, no chloride. At equilibrium, say a minute later, that's what I've got. I have no HCl left in that bottle. And they go, wait, where did it go? All of the HCl is gone. It's reacted with water to give me chloride ions and hydronium. Now, I'm going to do the exact same thing with HF. Put 0.2 mole per liter. These are 0. Wait a few minutes and measure it, and here's what I get. What does that mean about how much of the HF reacted? Very, very little. Almost none of it reacted at all. What I've got over here, 0.01 molarity, 0.01 molarity. So one way to talk about this is percentage. Gosh, 100% of the HCl reacted. Only a small percentage of the HF reacted. So if I wanted to talk about that in terms of how much reacted, we say percent dissociation. How much of that broke up? How much of that broke up? So if I wanted to have percent dissociation, would it surprise you if I did something like this over this times 100%? That's how much sort of dissociated, broke off, reacted, versus how much there was originally, and then just converted it to a percent by multiplying by a percent. Now, what's this percent dissociation going to be for a strong acid? What's it going to be for a weak acid? Well, for a weak acid, it's much less than 100%. That's what weak acids do. They don't do much. They get in the water, they react a little bit, they dissociate a little bit, but not a lot. And so we can say, well, strong acid, percent dissociation, it's effectively 100%. Now let's do some math and then we'll formalize this formula. But I think it sort of makes intuitive sense when we look at that example. Okay, so here's what we're saying. 0.10 molarity HCl, put it in water, I get 0.10 molarity H3O plus. I put 0.10 molarity acetic acid in water. I get 0.0013 molarity H3O plus. 100%, much less than 100% was converted into H3O plus. If I wanted to do that math, 0.0013 divided by 0.10. That's the amount that actually reacted. There's the amount I initially had in there. If I multiply that by 100%, I get 1.3%, and we say dissociated. Well, here's the actual formula. So acid dissociation equals the H3O plus concentration at equilibrium meaning you put the acid in the water, let it sit for a while, and measure how much H3O plus has been produced. And that's only been produced when the acid dissociates and makes that. And I can say that we compare to the concentration of the acid initially, or what was on the label. How much reacted versus how much was in there, and then to convert it to a percent times percent. But it sort of makes intuitive sense, but there is the formula if you want to strictly be able to follow that arithmetic. Now, we can do something really cool with this. I love this stuff. Now here's what I'm going to do. Acid, HBr, there's its conjugate base. Here's a base. There's conjugate acid. So I've got an acid and an acid. Acid, conjugate acid. I also have here a base and a conjugate base. Similarly here, HF is an acid. There's its conjugate base, fluoride. Sodium hydroxide we recognize as a base, and hydroxide's conjugate acid is water. Now, notice what's going on with the equilibrium. It's saying, well, there's an equilibrium, but it sort of favors that direction. Another equilibrium favors that direction. Well, let's compare, say, the acid strength. This is a strong acid, HBr. HNO2 is a weak acid. This is a weak acid, and water is a weak acid. But this is the weaker weak acid, and this one is less weak. Now here's what's going on. The strongest acid wins, the strongest base wins. So in both of these cases, stronger acid is driving the equilibrium. The less weak, stronger acid is driving the equilibrium. We can do the same comparison with bases, and we'll find the stronger base is winning. So here's one way to think about it. If I have a stronger acid or base on one side, I have weaker acid or base on the other side, I can think of it like this. The stronger acid or the stronger base sort of drives the equilibrium. So these can be acids or bases. So we can apply that right down here. HF, of course, is an acid. NO2 minus nitrite, its conjugate acid is HNO2. HF's Ka is about 10 to the minus 4. HNO2 Ka is about 10 to the minus 4. Very subtle difference there. HNO2 is very slightly stronger. So when I think about the equilibrium, the stronger is going to win. I draw my little arrow like that, saying the quote-unquote now reactants are favored. The stronger acid sort of drives the equilibrium to the left. And we could compare the conjugate bases as well, which we will do on the next page. Okay, so in terms of acid-base strength, relative strength, here's a little summary page for us, right? I've been telling you, memorize HCl, HBr, HI, HNO3, HClO3 or HClO4, and H2SO4. These strong acids always win. If they're on one side or the other, they're going to drive the reaction in the opposite direction, drive the reaction away from them. And the strong base for Chem 51 is hydroxide. Now, there's an implication here. If I have a strong acid or a strong base, there's not really equilibrium. It just goes all the way. You put a strong base or a strong acid, and it drives it that way. Now, if on the reactant side, on the reactant side, if I have a weak acid and a weak base, now I have the case of not much happening. As soon as one of them is strong, there's no equilibrium, drives it all the way. If they're both weak, then we have this wishy-washy condition. So this just emphasizes stronger acid, stronger base, weaker conjugate acid, weaker conjugate base, equilibrium favors to produce more on the weaker side, or the strongers drive it. I can think of it the other way around. If I have a reaction that produces a stronger acid and a stronger base, it's not very likely. The equilibrium lies the other way. Let's look at a couple of practice problems here. HPO4 2- plus OH minus. And I'm just going to put an arrow like that, saying, well, they react. PO4 3- plus water. And it's a proton transfer, so I'm thinking, oh yeah, okay, this H plus is going to here, gives me water. Removing the H plus here gives me phosphate. So here are two acids. And here are two bases. And I want to know, I can compare acids or bases, and either way, the stronger one is going to drive the reaction. Well, I go to my table and I find out that this is a stronger acid compared to water, which is the weakest acid we can have in water. I also know that, oh yeah, hydroxide, that's the stronger base. Stronger acid, stronger base. So I think of this whole thing as being driven that way. Just grabbed a Sharpie for effect, but it doesn't really look that good. So maybe I'll put an arrow this way and a very tiny arrow coming back. Same thing for this problem. It says, what's the reaction between HF and ammonia? Now, that's weak and weak. I don't know what it's going to look like. F minus plus NH4 plus. The conjugate pairs then, of course, are, there's a conjugate pair, and there's a conjugate pair. So I can think of acids, bases, and all I have to do is look up, by any source, look up the stronger. Well, let's see, I'm going to put table 10.3 is what I'm going to use to compare. Ka again for HF is around 10 to the minus 4. Ka for ammonium is around 10 to the minus 10. That's the stronger acid. And that means this whole thing is that. All right. So we looked at acids in terms of exchanging H+. Then we did a little stoichiometry. Then we said, well, what if we just put them in water? What makes acidic and basic solutions? And then that allowed us to sort out relative strength, and that allows us to do this sort of thing. The last topics in Chapter 10 are going to be pH and buffers. Really important stuff, but that'll be next week. Hang in there, we're almost done.